Alright, welcome back to particle physics and the Standard Model. This is lecture 40 and we spent a lot of time in the previous lecture figuring out how the charge conjugation operator works in order to see the CP transformation of the W boson interactions with quarks, right. And we saw that this was how the C transformation worked. Applied to the left handed and right handed spinners, you got a complex conjugate with some polymetric structure on, but then you ended up getting a right handed or left handed spinner instead, okay, respectively. And then we saw that the mass term was left invariant under this operation, right. We worked that out carefully, but in that process we learnt about Grassmann numbers. We learnt that you have to populate two spinners with anti-commuting variables, okay. That is the only way you can get wave functions for fermions that are antisymmetric under exchange, okay. And when we applied that property, we indeed got back the mass term intact as we would expect, because charge conjugation has no business changing the mass term, right. There is nothing to do, it is nothing to do with that. And now we applied it to the W boson interaction, but the term with the phase, the e power I delta term, and once again we made use of some we made use of the Grassmann number anti-commutation relations as well as some special properties of the poly matrices, and we ended up getting a transformation that looked like this. But ultimately our goal was to check the CP transformation. So we also hit what we got as a result here with the parity operator and just flip the left and right handed spinners. So that ultimately if we took the entire interaction term involving the phase up and hit with the CP, we got back a term that looked very similar except with the phase flipped. So clearly that shows that if delta is not 0 under CP, this Lagrangian piece is not invariant. That means the entire weak interactions are not invariant under CP, correct. So very good, that is where the notion of there being at least 3 generations giving rise to CP violations in the weak sector, okay. And then we just began to saw the notion of flavor changing neutral currents, because everything we have been talking about was flavor changing charge currents involving the W, but what about neutral currents involving the Z boson, okay. And once again to inspect that we have to start with the flavor basis, where the Z boson marries off fermions from the same flavor. That is why you have repeating flavor index I in this case, and to really see whether there is any flavor changing going on, we have to go to the mass basis, correct. So in the mass basis, okay, remember we rotated the quarks, right, using matrices like these. Do you remember this, where so maybe I am not using a consistent notation. Remember where so okay, let me call this with a prime. These were 3×1 in flavor space, right, and then we hit it with unitary matrices, right, again acting on flavor space in order to rotate the quark fields into the mass basis, correct. Now what happens if I do that here? So, what would happen is the quark, I would basically, let me just write this down, okay, so that it is clear. I am now going to write it in, I am not going to put the I index, I am going to write it in terms of the 3 cross 1 itself, okay, in flavor space. So, I would end up with basically up to these coupling constants, I will have an LU dagger that rotates into the mass basis, correct, this is the mass basis, and I will have an LU sitting outside, right. What did that LU do? That was the one that rotated the UL over here, and of course, the sigma U bar and the ZU go for a ride, they just contract each other, right. So, of course, I should be careful about covariant and contravariant indices. Okay. Now, what is this? That says unity, right. And similarly, what will I have here? What is this term? Once again, I would rotate it such that I have an LD dagger, LD sigma bar mu Z mu DL dagger, and what is this again? That is also unity. Okay. Remember, when we had charged currents, right. So, recall when we had charged currents, we actually had something like LU dagger LD actually, okay, because on this side I had a UL dagger, but then on this side I had a DL, right. So, I still ended up with a matrix that in general is not unity, and that was indeed the CK matrix, okay, but I do not have that luxury now. So, it is not a luxury, I do not have that property here. In fact, I do have a luxury that whatever be the rotation matrix that takes me from flavor space to mass space, it is eaten away, and then I ended up with just identity, okay. So, I can now write that there is no CK matrix that takes me from one flavor to another for FCNCs, okay, or rather to be more precise for Z boson interactions. Okay. And of course, we explicitly saw, okay, that in the Higgs-Yukawa sector also we did not have this, right. Remember when we rotated the Yukawa matrices, once again all the rotation matrices ate each other and we got an identity, correct. So, you can convince yourself that for photon interactions also this is the case, okay. So, go from the flavor basis to mass basis, convince yourself that all those rotation matrices do cancel each other, okay. They do not really cancel, they basically go to identity, okay. So, the claim then is in the standard model there are no flavor changing neutral currents at tree level, okay. This is a very important statement, has very important consequences, okay. So, why do I say at tree level? Because What does this mean? Let me draw some simple diagrams to show this. I cannot have, for instance, a muon going to an electron spitting out a Z boson. Okay, this is not there in the standard model. Similarly, I cannot have an up quark going to a charm quark, okay, or rather the other way around, does not matter, a charm quark going to an up quark, because that is what is kinematically allowed by spitting out a Z boson, a virtual Z boson. Okay, that is also not allowed. See, its flavor changed, but it is still neutral, right, unlike with the W boson interaction where you have a flavor change, but with a charged vertex, correct. Okay, but it also means I cannot have a muon going to an electron spitting out a photon either, okay, nor a Higgs. Okay, that is what this statement generically means. At tree level there are no flavor changing neutral currents. So again, now let us inspect that phrase at tree level. Why do I say at tree level? Because I can always have a muon, okay, go to an electron, but in between it is turned into a neutrino. How can I do that? This vertex is there, right. So through the W vertex it is there, and from the W I can spit out a photon or a Z, okay. That is absolutely allowed, or closer to what we were doing. Let us take this vertex. So I can have a charm quark, okay. In the final state I have an up quark, but the charm could turn into a down quark, let us say, either a down quark or a strange quark or a bottom quark. Again I have a W. What is at this vertex? How would you describe the coupling at that vertex? There is a G2, but then you also have to multiply it with the relevant CK matrix element, okay. That is what this means, okay, and I can spit out a gamma. So this is also allowed. So see, at loop level in perturbation theory you can have flavor changing neutral currents, okay, in the standard model. However, charge currents you can have at the tree level itself, flavor changing charge currents, right. So this has very important implications, because that means that when you want to measure flavor changing processes, right, the rates are, so this just implies that the rates of flavor changing neutral currents in the standard model are very low, so low that we have not observed these yet. Why should they be low? Because if you have loops, first of all you are suffering from more couplings, right. You have just one coupling, but then you have 1, 2, 3 coupling at the amplitude level, and these couplings are all small, right, much smaller than 1. So that makes the rates go small, and the fact that you have a loop, the loop means you are losing out on some phase space. So you get phase space suppressions also, you are creating more virtual particles along the way, all that costs energy, all that costs in your transition rate, okay. You have factors of 1 over 16 pi squared for loops and so on, okay. Excellent. Now let us move on to something that I have slyly already introduced in these diagrams, which is a CK matrix for the lepton sector, okay. See, already I have made use of something here, right. Here I am saying that when you can have a mu going to a nu with a W, and I did not tell you what flavor that nu is, right. I am going to tell you that could be any flavor, just like over here you had any flavor, this could have been any of the 3 flavors. Why is that? Because all the machinery that we had now for the quark sector, by going from flavor basis to mass basis, you could apply all that again to the lepton sector also, okay. And I am going to write down to begin this discussion the lepton sector charged current. In fact, this is an exact equality. Okay, that is this. So, sigma bar mu W mu nu L E, and I am going to explicitly write down all the 3 flavors this time, okay. There is a good reason I am doing this. W mu, okay. So, these are all daggers, okay, not plus. Sigma bar mu W mu, but this is a minus, okay. And this, am I missing something here? Yes, I am. That is the Hermitian conjugate. Lagrangians are real, okay. Okay, good. So, why did I write this down? Okay. So, if I want to go to the mass spaces, okay, in principle, right, I can rotate, okay. So, let me put this towel, right. I can rotate this with some let us call it LE matrix, okay, and then go to, I can always do this, right. I can always rotate and go to some mass basis where I have this, okay. And of course, I can also rotate the neutrinos as well, right. So, I have this, I have this, I have this, and I can rotate this to go to using some matrix, of course, right, just like in the quark sector. In the quark sector, we rotated both the up and the down, correct. That was the generic thing that one we could do. But actually in practice, I am not going to do this, okay. Nobody really does this. The reason is that in the quark sector, right, the quark interactions are harder to measure, okay, than the charged leptons. What are the charged leptons? The E and the mu and the tau, okay. So, why is that? Because quarks are not isolated, remember, right. So, quarks are confined. So, that is because quarks are confined, right, because they are too heavy, some quarks, right, like the top quark and the bottom quark. So, too heavy to produce and study. Okay. So that means it made sense to distinguish, right, between the flavor eigenstate and the mass eigenstate. right, for both up type and down type quarks. Okay, agreed? But we do not actually have such a difficulty for charged leptons, right? You can literally what you see as what interacts as the electron is literally also what you would take as the mass eigenstate. Why? Because electrons and muons and tauons can be free, right? They are free actually, right? So, let me write down no such difficulty for charged leptons. Okay. So, absolutely, you know, when J.J. Thomson discovered the electron, right, did he discover the flavor eigenstate or the mass eigenstate? It was both actually, okay, both at once. Okay. So, when we call something an electron, right, we mean both the flavor eigenstate and the mass eigenstate, right. We do not need to distinguish this in the charge sector. Okay. All of this is to say that if there is a CKM matrix, right, for the leptons, for leptonic sector, right, it is all rotations in neutrinos. Okay. So, all the, by rotations I mean flavor space rotations, not real space rotations of course. Okay, put everything in the neutrino sector. Okay. This makes sense because neutrino flavors turn out to be easier to measure than mass. So, we will see soon why this is the case. We will see how masses are measured, etc., and we will indeed see that neutrino flavors, it is in the flavor or interaction eigenstate that we see the neutrinos all the time. Okay. Now, let me bookend this discussion by showing you what we mean by all this. If let me just show you the quark sector one more time. Okay. Let us go to a doubly boson interaction. Okay. So, where did we write down the CK matrix the first time? Somewhere here, right? Okay. So, here we have it, right? See, when we went from the flavor basis to the mass basis, I rotated the ULs, that is why I wrote it in a different color, right, and then I had an LU dagger sitting outside, and then I rotated the down quark and then I had an LD, right. I could also have, there was another choice I could have made here, which is I could have, let me just write this is important. So, could have just said that the mass basis UL dagger, right, is the same as, say I am switching colors, notice the green is mass basis, the blue is flavor basis or interaction basis. I could have just said these two are equal, then what would have happened? That means all the flavor space rotations are in the down type quarks, down type sector if you want, right. In other words, I could have just defined the CK matrix as going from, you know, the DL, right. If I just go from here to here, this I could have just called this the CK matrix, right, that is literally what this is, right? All the rotations are dumped into the down sector. So in fact people do use this convention, okay. Some people do take the CK matrix as rotations completely in the down sector. It is completely consistent for all the calculations that we want to do, okay, and assume that the up sector does not rotate at all. You will notice it is completely consistent. Other people will keep the down sector unrotated and put all the flavor rotations in the up sector and define that as a CK matrix. In this case CK matrix dagger, okay. So that is the sort of thing we are doing here, but in this case this kind of a structure is forced upon us because the charged lepton mass eigenstate and flavor eigenstate need not be distinguished. You can clearly detect them, and also the fact that for neutrinos it is actually you do not even actually know what the mass basis really is. You do not detect them in the mass basis, you only do it in the flavor basis, okay. And I would even argue that the second reason is stronger, okay. We will see all this pretty soon, okay. So we are going to write down the CK matrix equivalent of the neutrino sector now. So I am going to give a Yukawa interaction to the neutrinos. There is a Yukawa sector one could write down. So it looks like this. Again the I and the J are in flavor space, okay. So I have this, and once again I have to make use of the H tilde here. Remember what H tilde was? I sigma to H star, okay. And this is one way to give mass to the neutrinos. See what I have done? I have introduced a right handed neutrino, right. So this is not the only way. So let me just write down, not the only way to give mass to neutrinos, but we will go with this now, okay. This is good enough for our discussion, okay. So how would the mass go now after symmetry breaking, after ultra-weak symmetry breaking? I would have V times this, correct, and then nu Li dagger nu Rj. So expand the LL, right. The LL contains basically this is what, neutrino and electron, right. So that is the expansion I am putting in here, okay. And this, if I want to switch to the mass basis, I get what? Once again I am going to switch to the tilde notation we had before. Tilde means it is a 3×1 matrix in flavor space, okay, do not forget that. So M nu is now the mass matrix. So M nu is something that I obtained from L nu dagger, which was something that rotated the left handed neutrinos. Y nu, of course, to get the dimensions right, let me divide this by V, and R nu, something that rotated the right handed ones, okay. Now what would happen to the W interactions? So I am going to write this down and wrap up this lecture. We will take up the new matrix in the next lecture. In the mass basis, so you know, I am going to assume you know how to write this in the interaction basis. We saw it again and again for quarks, right. But in the leptons, I am going to skip writing it in the flavor basis. You absolutely know how it is. If not, you can see how it is now. Again, to be consistent with earlier convention, I am going to write the mass basis fields in green. For the charged leptons, it is the same, okay. So I have sigma bar mu, W mu minus, now the rotation here if I want is an LE dagger, but I do not need LE dagger. LE dagger could just be unity, okay. Let me just write this could be just unity. Then I have L nu, okay, Ij, again because it is the mass basis I am going to write nu L j, okay, in green, plus the Hermitian conjugate, okay. And now this Ij stands for mass basis index, and I am going to conclude this lecture by writing down the mass basis in terms of the flavor basis, okay, and that matrix that I hit it with is called the PMNS matrix, okay. In fact, if I am not wrong, this is not really the PMNS matrix, it is the Hermitian conjugate of the PMNS matrix, okay. Nevertheless, the physical picture stands. Instead of the CK matrix, we have the PMNS matrix, and of course, this is also supposed to be unitary, okay. So, I will leave you here. In the next lecture, we will see how to parameterize this matrix, understand some more things about it, and then talk about the unitarity of these matrices, okay. All right, see you in the next class. Thank you.